I'm really bit concerned about my topic is maybe too specific. And actually, I'm more in the industrial side, okay? But we are interested in using mathematics, okay? We are studying mathematics and developing algorithms to solve the mathematical formula more efficiently, okay? And myself is a fluid mechanician, especially I'm interested in the flow physics in mechanical engineering systems, especially we call it energy and propulsion systems. For example,
that's on the top, isn't it?
Yeah. This is everybody knows this is wind turbine, and the performance and stability of this energy system is dominated by the turbulent flow around this wind turbine. And also this is a sort of energy conversion process, jet engine combustor. And this is actually simulation result. We solve Navier-Stokes equation with chemistry. And for efficient mixing and combustion and the low emission production, we really need to fully understand what's going on inside of this turbine engine combustor. And this is a recent study working with Boeing. They are interested in controlling turbulent flow over aircraft wing. The main purpose of this research is to enhance the lift force when they take off or landing. Okay? So my research goal is to understand the flow physics around this energy and propulsion systems. And especially, I'm using supercomputers, okay, as we call technically computational fluid dynamics. And my goal is to have a true prediction, not validation of simulation results, okay? So some of you may understand what this means, okay? Most CFD, most computational fluid dynamics, we really have very nice cases which has experimental data such that we can validate our simulation result. This is not prediction, this is validation. But to be able to use this technique for real design, engineering design, we really need to have that capability prediction. Okay, this is a very nice flow chart I got from Boeing. They say the computational fluid dynamics actually transformed their design practice. For example, in US, the fundamental research actually started from doing some research in the national labs. For example, NASA. They developed sort of nice tools in mathematics and computational science, all these stuff, and then transferred to the industry. And then industry utilized this tool to design their own product. For example, in 1980, the Boeing developed Boeing 767, and then at the time they needed about 77 prototypes to design this aircraft wing. And then the computational tool developed and even better and better, and then they also aircraft performance improved significantly. And then in 2000, around 2000, they needed just about 10 prototypes. This is a really significant reduction of the design cost. Okay? Now they have about 5 prototypes, but it is questionable whether they can reduce this number even smaller. Okay? And the major issue in the Boeing here is that they want to have enhanced stability and more maneuverability, especially in the growing market for the military applications. And then they see that the turbulence, which is governed by Navier-Stokes equations, nothing but the mass conservation, momentum conservation, and energy conservation. Okay, so they are interested in understanding this flow physics using a computational tool and the computational mathematics. Okay, This is a recent report published by the American Airline magazine in, I guess, it's 2008. They reported what they did. Actually, they had a aircraft which was developed by Boeing. It's 737. It was developed from 1967, and then still is a major aircraft in the domestic. And then they don't have so-called winglet. They have a sharp tip. And then recently they added a so-called winglet, and then found this change, this very simple change, reduced about 400,000 tons of carbon dioxide. And then this is about 25 million gallons per year. This very small change. And then this change was possible based on the understanding, better physics, better flow physics of what's going on the tip of the wing. Okay. Now, so I don't want to go to technical part in my research area, but just give us some idea of what's going on in this field. As I mentioned, I'm fluid mechanician, and then I'm more interested in the turbulent flow. Okay? And then everybody knows by the name, by turbulence, it's chaotic and stochastic. But it's not truly random. Okay? The turbulent, any question?
Agreeing with you.
Yeah. Okay. So turbulent flow is essentially composed of eddies. Eddies is nothing but the fluid motion. Just imagine it's swirling. Okay. And then these eddies have different lengths and time scales. Okay. And this plot is nothing but the sort of a scaled plot of turbulent fluid motion in terms of wave number and then energy. Okay. And the wave number is just one of a length scale, right? So this is a large scale fluid motion. Okay. So large scale fluid motion essentially has a bigger energy. Okay. It's a big swirl, has a big energy, right? And this is a small scale motion. Small scale is a smaller energy, right? It's quite natural. And then theoretically you can prove all turbulent flow, fully turbulent flow should follow some sort of a scaling law. Okay, we can mathematically prove this. Okay, and then there's a little bit difference in the large scale motion. This is because of the geometry. Okay, the large scale motion is really the function of geometry, but the small scale motion is only the universal. Okay, that's the key of turbulence modeling. We solve this large scale motion accurately. Okay, but if you have a good model which can account for this universal scales, then we can save significantly the computational cost. Okay, this is the idea of my computational technique. Okay, so there are three major techniques in the computational fluid dynamics. So-called the direct numerical simulation, is the name indicates, which it solves the Navier-Stokes equations without any turbulence model. That means the mesh, the computational grid, should be the smallest, should be smaller than the smallest eddy motion. Okay, so it resolves smallest continuum fluid motion without any turbulence model. So this is very expensive technique. Okay. And Reynolds average Navier-Stokes simulation is nothing but to take a time average of your Navier-Stokes equation, the momentum equation and continuity equation and the energy equation. In that way, we just remove all the scales and we model these all scales using a turbulence model. Okay? So it's a simplest approach, but essentially has some limitations, especially if we reduce the aircraft wing prototypes. Okay, that's the major function of major issue there is turbulence. Okay, and then in the case, this technique is really limited. For example, large-scale mixing, stirring and engulfing, and the pressure fluctuations, noise, and emissions. These things are really difficult to predict using a conventional turbulence model technology. Okay, this is actually the current state-of-the-art technologies in most of the conventional and commercial CFD tools. Now, recently we are looking at this new technology, relatively new. Okay, it's about 20 years by now, and then we call this Large-Eddy simulation. And then just remind you about this plot. We, based on this scaling law, okay, we solve the large-scale motion directly. Okay, the grid spacing is small enough to resolve the large energy-containing turbulent fluid motions. And then we model only the universal small-scale turbulent fluid motion. This is called Large-Eddy simulation. Okay. This is nothing but the scale separation using a filter. Okay. So the filtering is one of the key issues in the Large-Eddy simulation. This is a filter operator, convolution. G is the filter. Okay. And then U is the instantaneous velocity component, and then this convolution integral give you this is something like a low-pass filter. Okay. For example, the red line here is the actual turbulent flow. Okay. And then by taking a low-pass filter, we have a large scale of fluid motion, and then the small scale oscillations is clipped out. Okay. And then this is a momentum equation, nothing but the momentum equation of fluid motion. And then by taking the bar is a filter operator, we have additional term, which is coming from the treating this nonlinear term. Okay, this we call subgrid-scale stress tensor. This is nothing but the term we need to model because this is nonlinearity. This is turbulence closure. Okay? The idea is that again we resolve large-scale fluid motion. Okay, but high-frequency, small-scale turbulent model we use subscale turbulence model. Okay, this is actual simulation, but during numerical simulation, you see that even very small fluid motions are captured by a computational mesh. And then this is LES flow field. The large scale motion is actually the same because I just filtered this field using a low pass filter here. Okay. So in the industry, especially in the aerospace and energy industry, they are really interested in this large scale motion. Okay. With the small scale fluid motions, there is too much.
Presumably you want to design the plane so you get rid of that large scale motion, is that right? In terms of aircraft?
Yeah, essentially what they want is correct lift curve as a function of angle of attack and the flow condition. Yes, but I will show you that even that primitive integral quantities is not correctly captured using a conventional tool. Okay. So this is a little bit detail about the turbulence modeling, and we use so-called eddy viscosity model, which is based on the Bushnell's approximation, and something like making an analogy of turbulent mixing to a molecular mixing. That's it. Okay. Yeah, this is the state-of-the-art technique at the industry. I'm working with Boeing, and then my program officer just sent me this plot. Okay, this plot is nothing but the lift coefficient. Okay, so if you multiply the density times velocity square, then you will have a lift force. Okay, and this is nothing but the angle of attack. Okay, so this is just the angles of your aircraft. Okay, if you have a high angle of attack, you will have a higher lift. So this is typically the situation in the takeoff and landing, right? And the red, most of these lines are Ray's results, the Reynolds and Navier-Stokes results. And the black line is experimental data. And you see, some people may say this follows quite good. Okay, the results are not bad, but it's tricky because they are playing with around this area. We call it the store. So they really want to improve the angle of attack, which occurs stall. But without correctly predicting this stall, doesn't make sense in the computational area, right? So the stall prediction is the key there. And the red is the recent LES, Large-Eddy simulation result. Okay.
That's in degrees, the horizontal axis, isn't it? The alpha is in degrees.
Yeah, they do it, yes, yeah. Typically,
Checking.
yeah, they have about 20 degrees, and then beyond this angle, they will have a stall. The aircraft will drop the lift force.
So the LES is very good.
Yeah.
Still.
Yeah. And this is one of the reasons why the conventional tool is not accurate enough. We call it there is something happen on the blade surface. We call transition, which is laminar flow, very well-defined laminar flow, becomes unstable and then becomes turbulent. And then this point we call transition. And the conventional tool is actually solve the Navier-Stokes equation assuming that there is always turbulence. And then some tricks is that they can specify there might be a transition. But a priori, we don't know where the transition is. Okay? So the conventional tool is really limited to predicting these transition locations, and then we found that the correct prediction of transition is the key of this flow prediction. The LES actually are quite good in predicting the location of flow transition compared to the experimental data. You see that there's a smooth streamline. This is a skin friction, nothing but the drag on the surface. And then this smooth flow is suddenly becomes turbulent, and there's a sort of hot spot, because this is qualitatively the location of transition. And the problem here is that, as I mentioned, we were able to refine our grid until we get good result. Okay? For example, the symbol here, the blue and here red is experimental data. And then the first shot, we used 24 million mesh points to simulate the flow I showed. And then I got the result, which is not really great in terms of the pressure distribution on the surface. If you integrate this pressure, then you will get the drag and lift force. Okay? And then I doubled the mesh point, and then finally I got the very nice solution. Okay? This is validation, not prediction. Okay? I need the data to validate my simulation result. Okay? This is the state-of-the-art Large-Eddy simulation. Okay? The major reason of this dramatic change and the mesh dependency is coming in the from the prediction of transition location. Again, the transition is the key issue in the turbulence prediction. Let me ask you case. So which turbulence simulation seems correct? Number 1 and number 2. What do you think?
Number 1 looks better because it looks messier. So I imagine it should be perhaps
right. There's an even smaller turbulence case, yeah. Right? It would pretty much look like a well-resolved simulation, right?
Yeah.
Okay. And here, this is number 1 case and number 2 case. The red line here is the number 1. Blue lines are the number 2 case. Okay. And then the symbol is experimental data. Now, number 1 is great simulation, right? It's better simulation.
Yeah.
Right?
Yeah.
We spend 10 years. If you refine your mesh, if more and more, your solution closes to the second case, not going to the number 1. So we cannot validate our simulation result. It just gave up. And later, about 10 years later, there were new, okay, this is something like we use the very coarse mesh along the span. Okay, that means we cannot resolve the large-scale motion correctly, but the comparison is better than the refined simulation. This was a puzzle. And then later, other experiments found that the previous experiment was wrong. We spent just 10 years to predict the wrong result, okay, to validate over the wrong results, okay. So this is the motivation. We really need a sort of uncertainty quantification in our simulation. We cannot rely on experimental data anymore, okay.
So your noisy computation matched the noisy experiment. Yeah, vibration, yeah.
For example, in this case, the reason we have smaller scales in the area is noise and numerical address. Simply.
Yeah. And the experiment, there was vibration.
Yeah. Yeah. Exactly. Yeah. All the times experiments, they couldn't control the inflow condition and wall roughness actually. Yeah. And then later we found this flow is really, really sensitive to that conditions.
So it's like a jump, quite a jump, discontinuous jump in the behavior.
It's not a jump, but we call it subcritical Reynolds number. And then in the Reynolds number is nothing but the ratio between the inertia and viscous force. Okay. If you have a high inertia, then your flow tends to be more unstable. Okay. So this Reynolds number, the flow in that Reynolds number is really, really sensitive to the inflow and boundary conditions. That was the problem. And another example, we are conducting, recently we published in the Turbulent shear flow phenomena. This is a real jet engine of Airbus 318, okay? And this is the Pratt & Whitney, technically Pratt & Whitney 6000 engine developed by Pratt & Whitney. And they lost about $4 billion because of this engine. And then fired about 100 people related to this project. Okay. The reason was that they wanted to reduce number of blades inside of engine, and then computational prediction told that's okay, it works. And then they made a prototype, and then make an experiment, making a one prototype and then conducting a full experimental validation require about $4 billion for this engine. So they came to us actually when I was at Stanford, okay? And then this work was done at Stanford, and that is Carnegie Mellon, okay? So this is a Large-Eddy simulation of turbulent combustion inside of an engine, okay? For this, we actually account for about 1,000 chemical reactions, and then I don't show here. Okay. So if you see here, it's not clear, but we also have a spray particles, which is a liquid fuel injected through the bore. It's about 70 million to 50 million particles. We track using a Newton's second law Lagrangian way all the particles, and we account for collision and evaporation and condensation. Okay, and then we integrate all of these components to make this simulation. Okay. And then we had a sort of a comparison with the experimental data that Pratt & Whitney had. And luckily, it was very easy validation. You see that what they could measure is just 5 points at the engine of the engine. They couldn't see anything inside of the engine before this simulation. Because the temperature is really high and the geometry is relatively small, no probe can go inside. Okay, what they could measure is just these 5 points, time and temperature. And then this is a mean temperature and NOx emission comparison with experimental data and LES. I cannot show you exact number because it's classified for them. Okay, but in general, the comparison is pretty good. And then if we increase the mesh resolution, the area solution close to the approach to the experimental data. Okay, so it was very nice simulation. And the major problem there was that they couldn't understand, based on this mean data, okay, they couldn't understand why their turbine is located just downstream of this combustor break down so easily. Okay. So this is some sort of qualitative explanation why the turbine blade just behind of this combustor suffer from the thermal fatigue because of there was a dilution hole which give you cold air inside of the engine to cool down the jet. Otherwise, your turbine blade will melt down. Okay, and then this interaction actually produce so-called Kalman vortex type vortical structures to downstream, and then this introduce coherent time-dependent thermal hot streams, and then this hot streams is not well measured in the experimental tool. That was the problem. So they typically have some sort of safety factor based on this data, and then designed cooling system in the turbine. And then it was not actually enough for their new engine. Okay. And I myself simulated this part. It's a very small part of the engine, and then some other people actually simulated the flow around the compressor and the turbine. And then we combined all of these components in the computational world. This is a whole engine simulation. Okay, we use MPI and then communicate information, flow information, communicate through the MPI tool using multiple CPUs. This is probably the velocity controls around the engine, and the CTO at Pratt & Whitney told us that this is like something like going to the moon. Okay. So I say there are huge amount of mathematical effort there, but our service is mostly in the end user part. It doesn't really drive much mathematical equations, but we try to discretize this equation more efficiently in a more stable way, and then we try to reformulate the equation in a more conservative form. Because the major goal to us is to conserve mass, momentum, and energy. Okay. Again, let's go back to the validation issue here. Okay. So the current LES, this is not the tool which you can use to predict something. This is neither sort of validation. Okay. So the idea here is that we want to improve the Large-Eddy simulation framework to have a sort of self-verification capability. Okay. As I mentioned, the LES, Large-Eddy simulation, is simply based on the separation of scales, large-scale motion and small-scale motions. So if you have a smaller grid, okay, and smaller filter width, that means you will resolve smaller scales more, and then model even smaller scales, right? So if you refine mesh more and more, then the solution will convert to the direct numerical simulation result, which is the solution without turbulence model, right? So this is not true solution we call Large-Eddy simulation solution. This is direct numerical solution, right? The verification is nothing but the issue whether we solve the equation correctly, right? But this mentioned refinement is give a correct solution, but this is not the solution of your Large-Eddy simulation equation. This is a simulation, a solution to the direct, without filtered Navier-Stokes equation. Okay, so it was really difficult to verify whether we have a correct model in our simulation. For example, this is coarse mesh simulation, fine and finer. And then you will see that smaller and smaller scales are resolved on the mesh, and the solution converts to direct numerical solution, not Large-Eddy simulation equation solution. Right? Okay, so this is LES governing equations. Okay, for incompressible flow, this is mass conservation, continuity, and this is momentum conservation. Okay, and this is a subscale turbulence model I mentioned, the subscale stress tensor. In the conventional LES, actually we don't perform any filtering. We just simply assume that the solution we are solving is already filtered using a grid size. This we call implicit filter. Okay? That's the reason why the solution, any solution, is highly dependent on the grid spacing. Right? And then, as I mentioned, more scales will be resolved with grid refinement, and there will be no grid converged solution. If we do have a grid converged solution, then the solution is direct numerical equation solution. Okay, not this equation solution. Okay. And also, one of the key drawbacks of this approach is that this turbulence model, okay, the modeling this turbulence term is highly affected by the numerical errors. That's because conventional CFD, we use low-order computational the discretization scale, second order, third order, fourth order maximum. Right? In that case, for example, this is an exact function, and then if you make a derivative of this function in terms of x, then you will have the coefficient of ik. This is called wave number. Okay? But if you apply a second order central difference scheme to this equation, then you will have modified wave number. This is simply the sine k delta x over delta x, something like resolution of your scheme. This is a plot. If you have an exact wave number, you will have a linear, right? This is the exact versus k. K prime is exact, then you will have a linear. But because of a numerical error, second order central difference scheme deviate from the exact solution at high wave numbers, right? These are the numerical errors, and these numerical errors included in your turbulence model. Again, this is a simplified energy spectrum of your turbulent flow. Okay, this is a filter width. Okay, and then I will resolve this large scale motion, and then I would like to model this small scale, small portion. But the problem is that in the low wave number, large scale motion, as I mentioned in this plot, we don't have much error, right? This area we're really quite accurate enough. So this motion is relatively well predicted, large scale motion. But in the small scale motion, contaminated by numerical errors. Okay. So now we want to take an explicit filter of the equation, especially in the nonlinear term, because this nonlinear term will produce smaller and smaller eddy motions. Okay, so the idea is that we will discretize our governing equation on a final mesh. Okay, but keep your filter width to keep your resolved scale is the same. And that way, you can reduce the influence of numerical errors on your turbulence model. Again, your discretization is performed on a baseline grid, but you will model your turbulence, which is filtered mesh points. Okay, that's the idea. So, if we take low-pass filter, explicit filter of this, then we discard this contaminated noise from your turbulence model, and then use only the information which is accurate enough. Okay. That's what we call explicit filter ADS. This is a traditional ADS on a 32 cube mesh. We have a box. Okay, this is a flow through a turbulent flat plates. Okay, we call it technically channel flow. And this is a explicit ADS solution. Okay, we have a 64 cube, a 128 cube. Okay, in the conventional technique, if you refine your mesh gradually, then you will have gradually resolved smaller and smaller scales, right? But this scales as a numerical errors, right? Now, even though I have a final mesh, I will fix my explicit filter width. It's exactly the same size of this. So that's the way we have roughly the same large scale structures right? And then model the small scale eddies more accurately. Right? The idea is separate physics turbulence modeling from numerical errors. Okay? And then in this way we can obtain a grid independent eddy solution. Now we can verify whether I am solving the equation correctly. Okay, this is the different story whether I am having good result, right? This is a validation issue. So if your solution is not corresponding to the good experimental data or the numerical simulation data, that means your model is not good. Because now your turbulence model is nullly numerical error free, right? So this is a quantitative validation of this methodology. Okay, the solid black line here is the direct numerical simulation data filtered with the same explicit filter width I used for LES. But you see that there are 3 different lines with the mesh refinement. But as I mentioned, I have a same filter width, and then you can prove the solution converts each other for just LES solution, not two DNS. Right? So we have a grid converged solution. But the solution is not that great on that given filter width. This is the capability of the current turbulence model. Based on this information, we have a room how to improve our turbulence model more accurately. Right? So refining your mesh is technically, in simple geometry is not that difficult, but if you have a complex geometry, it's really a big burden. Okay? So we are currently working on to implement additive mesh refinement technique, which, because for example, this guy has a fluid motion. This is not turbulent anyway, but essentially the turbulent vorticity actually concentrates in the small portion of your computational domain. So there is no reason to refine it everywhere, right? So this is the research I'm working on these days. Okay, so this is my summary. Okay, this was my research goal. Is nothing but to utilize and design and develop a computational fluid dynamics tools to understand flow physics in the energy systems and propulsion systems. And now we know that we are heavily relying on experimental data still. Okay? For us, as a computational scientist, we really need a tool which is really predictive, which is not relying on any experimental data, to give a better idea how to design innovative, which wasn't been there. Okay? And then, for example, very extreme condition, very high temperature, high pressure, as I shown in the jet engine, the current experimental technique is not that capable. Okay? So we have a really high need of a high fidelity prediction, computational prediction tool, and huge room for improvement, especially in the computational mathematics. Thank you, and I'm glad to have your questions.